Hi folks, we're going to be talking today about standard deviation and how these data sets that we're looking at actually vary. So here's an example of something that might come into play with standard deviation. So say we're talking about income disparity appearing across the nation's broadcast, and Clark Kent wants to get to the heart of the matter and look at the mean income from households in the United States. So assume that he polled 1 million people, and Clark found that the average salary in 2015 was $75,000, and it's up only slightly from the mean salary of $74,750 in 2014. So does Clark have enough information to talk about income disparity? Well, most people will say, oh yes, this is enough to talk about it, but actually this is more of a bait and switch here. So what's going on is Clark hasn't really addressed the issue of income disparity at all. What we're looking for is how things vary from, in fact, the rich to the poor, essentially. And so to give you an example here, the way we could look at it, say we had a first data set and we had the mean being 75,000 as we had up above, we could have all the values of income being 75,000 for 4 people. Now, obviously we could stretch this out to 1 million, but hopefully you get the point. So now there's no income disparity whatsoever in this sort of data set. Whereas if we actually look at another data set, say 290,000, 4,000, 3,000, and 3,000, that actually has the same mean, but it's a much different data set. And look at the disparity between the incomes here. So that's what we want to try and address here, is this variance going on within the data set, and that's dealing with this income disparity question. So notice these are giving us a completely different picture. So that's what we're going to focus on looking at. How is the spread of a distribution? So to start, we'll actually start with 6 values and kind of see if we can determine how to look at the spread of a data set. So if we're trying to describe that, the first thing we do, we start with 10. We're going to need to subtract it from the mean. Essentially, we're looking how things vary from the mean. Well, we can calculate the mean. It's not too hard. In this case, if you add up 10, negative 14, 7, 13, 21, and 5, I believe you get, 42, so the mean is 7. In that case, so if we subtract that 10 minus our 7, notice that would finish us with 3. And we can do the same thing for negative 14. So if we take negative 14 and subtract off the mean, that's what's indicated by the X bar there, by the way. Negative 14 minus 7, we have, that's negative 21. And we can continue this process for the rest of the data values. And notice, like, for example, the 7, actually, when we subtract that from the mean, that goes back to 0. But you can have numbers all over the board. And what do we want to do when we're trying to talk about how things vary from center? Well, we want to try and look at what all of these differences happen to be. And the way we look at this is actually looking at a sum, and that's what the sigma notation is right here. This means sum. So basically all we're doing is looking in that last row of the table and adding up these values. So if I add up 3, negative 21, 0, 6, 14, and negative 2, what do we end up getting? Well, we end up getting 0. So notice there is some spread from the mean here, but we get an answer of 0. In fact, if we just did the sum every time, no matter how large the data set, it will always equal 0. So we need to take a different approach in order to find how things spread from our mean. So with that in mind, how are we going to improve upon it? Well, rather than take just the difference with the mean, we're going to take the difference and actually square it. So now when we're plugging in 10, we're going to take 10 minus 7 and we're going to square that quantity. So that's basically 3 squared, which is 9. We can do the same thing with negative 14. If we take negative 14 and subtract off 7, square that, we actually get 441. Notice, actually, since we're always taking a square in our final column here, we will always have a non-negative number. So the worst case scenario, what I mean by that is 0, and then all the rest possibilities will actually be positive, because anytime you square a negative, you get a positive number. So when we keep on going on down the list, notice you're getting a string of positive numbers. Well, that tells us for a fact that when we take the sum, we will not get a negative number kind of balancing out. So as long as you have one non-zero number, you're going to get a non-zero sum. And that's the idea we take home here. So when we actually look at the sum, so looking at the sum of the last column, if you had 9, 441, 0, 36, 196, and 4, you get 686. And so this gives us a better approach. And this leads us to our definition that we're going to talk about. And it's called the sample variance. So the sample variance, which we'll denote by s squared, that provides us with a measure of the spread from center of a data set. And what we'll do is basically take that sum that we just took before, but we're going to divide the whole thing by n minus 1, where n is the number of observations. Now, this will vary slightly from what we have called a population variance, and that's going to be denoted by a sigma squared. The only difference between these two formulas is the fact that the sample variance actually divides by n minus 1, so we're subtracting 1 from the sample size, whereas the population variance actually divides by n. For our cases, when you think about population, usually when we gather information, it's not about the whole population we want to study, so most often we're dealing with sample variance. And that's what we're going to focus on here. But just want you to be aware of the difference in the definitions. But all of our calculations will deal with sample variance here. So moving back to our question, we had all our data values. We took the sum. Now what we didn't do is divide by the number of observations minus 1. So when we take the number of observations, notice there's 6 different observations. You see that from x1, x2, x3, x4, x5, x6 up at the top. So 6 observations, you subtract 1, you get 5. So now when we take s squared, you take that 686, which we found before, and we divide by 5. And so that gives us a sample variance of 137.2. Now, we were looking for this magical term called standard deviation. Okay? So if we're thinking of that, well, standard deviation, what we need to look at is basically just take that s squared, and we want to take the square root of both sides. So what that gives us is our sample standard deviation is actually the square root of that sum of the squares of the differences in the mean and the observation values, and we divide all that by n minus 1. And a similar sort of population standard deviation definition can be given. Basically, the only difference here will be instead of dividing by n minus 1, we're going to divide by n. Just like before, where we focused on sample standard deviation or sample variance, we're going to focus on sample standard deviation from here on out. But just be aware that there is such a thing as population standard deviation if you have every single individual that you want to study about in your data set. So keep that in mind. But everything here is just samples that we're dealing with. So now calculating that standard deviation, notice we had our value before for the variance. All we need to do is take the square root of that 137.2 that we talked about. Well, as soon as we punch in that square root button in our calculator, we end up with 11.713, or approximately 11.7. So now we have an idea of what a sample standard deviation calculation looks like, right? So let's take this one step further, go back to our income case. And in particular, let's look at the one that had some spread. So the 290,000, 4,000, 3,000, 3,000, and we were discussing income disparity. So let's see if we can give a value for that. So what's the standard deviation of that provided set? Well, we can start just like we had before and create our table where we look at the differences of the observation and the mean and then squaring that value. Well, when you take a look, you take 290,000 minus 75,000 squared. This number is going to be so large we can't even fit it on the screen real nice unless we write it in scientific notation. So that's what we're going to do. We're going to have a 10 to the 10th power times 4.6225. So similar manner is going to actually happen when we plug in 4,000 and subtract that from the 75,000 and square that, because 75,000 is our mean. And we're going to finish with a 10 to the 9th power in that case, times a 5.041. 3,000 is more of the same suit, and remember we have that for the last two pieces actually. When we take 3,000 minus 75,000 and square that quantity, we're going to get 10 to the 9th times a 5.184. So both of those last pieces, we're still at 10 to the 9th. So now, piecing all that together to find the standard deviation, what do? Well, we take the sum of the last column and divide by our number of observations minus 1. So what does that look like? Well, we have 4.6225 times 10 to the 10th, which appears in our first. And since all the others are 10 to the 9th, we'll just group all those together and add them. So you have 5.041 plus 5.184 twice. times 10 to the ninth, and then we divide by 4 minus 1 once again because we have those 4 observations, the 290,000, the 4,000, the 3,000, and the 3,000. So plug all this, it's just a plug and chug. Plug in your numerator, make sure it's in parentheses, divide by the denominator, which is 3, and then we take the square root of all that number, and we finish with approximately 143,000 and some change. So keep that in mind. This shows there's a large income disparity in this data set, and these are the types of things we're going to want to answer questions. We want to know not only the center, but also the spread of our distribution.